Hello, everybody. Welcome back to Mathematical Statistics. When we last left off, we were talking about Slutsky's theorem in the context of convergence in distribution. So Slutsky's theorem allowed us to combine convergence in distribution with convergence in probability through some kinds of simple combinations. So maybe we have a sequence converging in probability and another sequence converging in distribution, and we want to look at things like the sum of the elements in the sequences. So this has brought us to where we need to be to state and prove the famed central limit theorem. In statistics, the central limit theorem is everything. I'm sure you've used it if you've done any sort of even elementary statistics, and this is the reason everyone uses the normal distribution for everything, which I actually have issue with. One of the things that's so great about mathematical statistics is if you are making confidence intervals or building hypothesis tests using a Stat 101 textbook, it will have you assume that things have normal distributions when they don't. And in mathematical statistics, we're going to learn to do those same things with like a beta distribution or any distribution we want, named or otherwise. And so it's really going to free us up to stop assuming normality. But there is a good reason for it. And that is because you get this normal distribution out of averaging things. And that's what the central limit theorem is all about. So it's not crazy that people overuse the normal distribution. And today we find out why. So first up, I have a quick definition, and this is the definition of asymptotic normality. So this is a characterization for a sequence of random variables, x1, x2, etc. We say that x is, you know what, I'm not going to write the English out, but xn is asymptotically normal. So we're going to write this with our squiggly line has the distribution asymp, and then our normal notation with some mean that could depend on n, so like a mu n and some variance sigma n squared. So what I should have written, and I'm too lazy to write, is xn is asymptotically normal with asymptotic mean mu sub n and asymptotic variance sigma n squared. And this means that if you recenter this sequence of random variables about the mean, and you divide by the standard deviation, so rescale it as well, that this sequence converges in distribution to a standard normal random variable. That's what asymptotic normality means. So with this, we are ready to state and prove the central limit theorem. So here we go, the central limit theorem. I'm going to start off with a sequence or random sample, x1, x2 on up. And I'm going to suppose these are IID, independent and identically distributed, with some common mean. I'm not going to bother to write common, but if they're identically distributed, they all have the same mean and variance. So with mean mu and variance sigma squared. And for the central limit theorem, I do need to assume that the variance is finite, which is equivalent to the second moment being finite. And if any, like the kth moment is finite, then the lower order moments are finite as well. So by saying this, we also have a finite mean. Okay, I'm going to define a new sequence, Zn. I'm going to define Z sub n to be x bar, so that is the sample mean, and that does depend on n, so I might write like x bar sub n to really drive that home, but for some reason I'm not. Minus the mean for x bar, which is the same as the mean for the individual x's, divided by the standard deviation for x bar. So the variance for x bar is the original variance divided by n, and when you take a square root, the standard deviation for x bar is sigma over the square root of n. So under very, very few assumptions here, we just have IID and finite variance, and we actually don't even really need IID. There's different forms of the central limit theorem. We have that the Zn converge in distribution to a standard normal distribution, even though we don't have normality anywhere in this setup. These can be from any distribution, even a discrete distribution, as long as we have finite variance, and we're going to get this kind of convergence. So what this means in our new notation, i.e., x bar, the sample mean, is asymptotically normal with asymptotic mean mu and asymptotic variance sigma squared over n. And this is the reason that people use the normal distribution all over the place when there is actually no inherent normality in the problem. But again, in my personal opinion, they use it too much. And that's why I love math stats so much. We're going to learn how to do statistics with other distributions. So let's prove this result. It is a convergence in distribution result. And we learned last time that we can establish convergence in distribution through moment generating functions. The reason I want to use moment generating functions to show convergence in distribution as opposed to CDFs is because the ubiquitous normal distribution does not have a closed form CDF. We'll talk more about that soon, I think maybe even in today's class, but let's prove this using moment generating functions. So I have a caveat before we do that, and that is we're going to have to assume that moment generating functions exist. So that the moment generating function for each xi, they're all the same because they're identically distributed. We're going to assume it exists. The moment generating function is an expectation, which would then be a sum or an integral, and that could diverge and not be finite, and in which case we don't have a moment generating function. So this proof won't work, but the theorem still holds. It's just that using moment generating functions would not be the way to go. Our moment generating function for a random variable x is the expected value of e to the tx. And there's something else that we're not talking about in this class, but if you look at the expected value of e to the I tx, where I is the imaginary unit, then this is something known as a characteristic function. And it has all of the same great properties that moment generating functions have. For example, it does uniquely determine the distribution. It's just that I don't want to, I can't use them this semester because complex variables is not a prereq for this course. But if you do know about complex variables, you'd know that as a function of t, this function lives on the unit circle. So it's nice and bounded and it will always exist. So yes, you should really prove the central limit theorem using characteristic functions, which we're not covering in here. The second thing I want to assume, actually, let me add to this parenthetical remark, is, let's say, comma, and the second derivative of this MGF is continuous. I don't actually have to make this assumption because if the moment generating function exists in some neighborhood of zero, then it's going to be, its derivatives are going to be continuous at zero or in a neighborhood of zero. So both of these statements really should end, but now I'm feeling even more lazy. They should end with in some neighborhood of zero. So the t variable has to be around zero, a little bit to the left, a little bit to the right, or maybe a lot to the left and right, but some neighborhood around zero. So with these assumptions, we are ready to go. Again, these are assumptions that just make the proof a little easier and compact. They don't need to be true, but let's look at the Zn. The Zn is the sample mean x bar minus mu over sigma over the square root of n. I'm going to, excuse me, I'm going to flip that denominator up like this. I am going to multiply the top and bottom here by the square root of n. I'm just trying to massage this into a form that's going to work out well for us. So in the numerator, we're just going to have n, and in the denominator, we're going to have sigma times the square root of n, and then we have this x bar minus mu sitting here. Now, x bar is 1 over n times the sum of the x's, so if we multiply by n, we're going to cancel that 1 over n, and we're going to get the sum as I goes from 1 to n of xi, and then for the second term, we'll get n times mu. But actually, let me back that sum out and write the entire numerator as a sum xi minus mu, because if you run that sum through, you'll get mu n times, so that numerator is the same as the previous one. So we've rewritten the thing we want to show convergence and distribution for in terms of the x's. So next up, I want to consider the moment generating function, not for Zn yet, but for xi minus mu, which is a little strange. Maybe if you like, you could define yi to be xi minus mu, and you could rewrite this whole thing in terms of y's and be talking about the moment generating function for y or yi. I just don't feel the need to bring more notation into this problem. In fact, I'm going to drop this notation in just a moment. So this is going to be a function of t, and this is the expected value of e to the t times xi minus mu. So this is cumbersome, and we're going to be doing a lot with this function, like Taylor series expansions and stuff. So because of that, I'm going to drop the I'm going to drop this subscript. I'm going to call this m of t. And note we have some things we know about m of t. So m of 0 is going to be 1. Now that's true for every moment generating function. If you put a 0 in here, you get e to the 0, which is 1. The expected value of 1 is 1, so the entire thing is 1. Another thing to note is that if you take the first derivative and plug in 0, you will get the expected value of the variable, which in our case is xi minus mu. But if you run the expectation across, you get mu minus mu, you get 0. And finally, let's look at a second derivative evaluated at 0. You will get the expected value of xi minus mu squared, and this is the variance, sigma squared, which we assumed was finite for this problem. I am now going to look at a Taylor series expansion for m of t around the point 0. So I'm going to write m of t to be m of 0 plus m prime of 0 times t minus 0 plus m double prime of 0 times t minus 0 squared over 2 factorial. Let me just write one more. M triple prime of 0 over 3 factorial times t minus 0 cubed, dot, dot, dot. And I actually want to cut this off to a Taylor polynomial. So we can take a finite number of terms, with the last term being a special remainder term. So let's do that instead. We can write m of t as m of 0 plus m prime of 0 times t plus m double prime. Now I'm not going to write the 0. I'm going to put this 2 for 2 factorial and this t squared here. And you may recall from calculus that if you want to cut this off for an expansion about 0, you're going to put something else in here that is going to end up being somewhere between this 0, and this t. I'm going to call it c, and I'm going to say where c is between 0 and t. And I write that out the long way rather than saying something like this, because t could be negative, in which case we would have something like this, and I don't want to worry about it. So I'm just going to say between 0 and t, however they may fall. I do know that this is 1 and this is 0, so we get m of t equals 1 plus m double prime of c over 2 t squared, where c is something between 0 and t. Now I'm going to do something that maybe looks a little unmotivated. My reason for doing this is that we are going to kind of shrink the interval and let not quite see. I don't have a good motivation. Just bear with me for a moment. I am going to write this as m double prime of c minus sigma squared times t squared over 2. Actually would have a very good motivation if I did my next line first. But I can't just put that in there. I need to compensate, so I have to put a positive sigma squared t squared over 2 so that this line is equal to the line above. And with that, I am going to go back to the moment generating function for Zn. So let's go. The moment generating function for, because this was the moment generating function for an individual x in our sequence, x1, x2, etc. So for Zn is m sub Zn of t. This is the expected value of e to the t Zn. And Zn was a sum of the xi minus mu over sigma square root of n. That sum there is going from, as I goes from 1 to n. And you can pull this t sigma square root of n inside the sum, so that ultimately you have e to a sum. And e to a sum can be written as a product of e's. So this is, and if you know where I'm going with this, just go straight to the end. But this is the expected value of the product as I goes from 1 to n of e to the t xi minus mu over sigma square root of n. And by independence, you get to pull that product out. And by the identicalness of the distribution of the xi, this expectation is going to be the same for x1, x2, x3 on up. So we are just going to get the expected value of one of these terms to the nth power. Now, this is almost the moment generating function for xi minus mu. It's just that we have this extra thing in here. So you can think of the extra thing as attached to the t. In other words, this is the moment generating function that we're just calling capital M with no subscript, evaluated at t over sigma square root of n, all to the nth power. Okay, so this sigma squared t squared over 2, when I plug in t equals t over sigma square root of n, I get sigma squared t squared over 2 sigma squared n. And then for the final term here, I get m double prime. This m is the moment generating function for x1 minus mu. I'm evaluating this at some c sub n. This is divided by 2. And I keep going back to this line, and I'm trying to plug things into this line. So this is going to be minus sigma squared. And then for t here, I'm going to plug in the t over sigma squared of n. So I'll get t squared over sigma squared times n. So let me know if I should scroll back up and if there's anything I can clear up. And, oh, I should write explicitly for some c sub n between 0 and t over sigma square root of n. This is an expression for the moment generating function for z sub n. And remember, we're trying to show that z sub n converges in distribution to something, which you can show using CDFs. but in this case, it's going to be easier to use MGFs, and that's what we're doing. So we are going to let n go to infinity. And before I do that in its entirety, what's going to happen with some of these terms? Note that as n goes to infinity, this t over sigma square root of n is going to go to 0. And this is going to imply that this c sub n is going to 0 because it's squished between 0 and something that's going to 0. And here's where I want to use my assumed continuity of the second derivative of the moment generating function for x. This implies that the second derivative of the moment generating function for x evaluated at c sub n is going to the second derivative evaluated at 0. Right? If this is going to 0, you can put that in the function and it will be going to the function at 0 by continuity of this second derivative moment generating function. But remember that this second derivative evaluated at 0 is sigma squared. So all of that is to say that this is going to go to 0 as n goes to infinity. Okay, I am going to rewrite that moment generating function for z one more time. I'm just going to simplify a couple of things. So it is 1 plus, now for this term, I'm going to cancel the sigma squared stuff. And I have t squared over 2n. And then for this term, I am going to take that sequence that's going to 0 in there as n goes to infinity. I'm going to think of it as just like a sequence an t squared over 2 sigma squared n, where the an's are going to 0 as n goes to infinity. So I just paused because I realized I forgot. Back here, this nth power, I didn't put it on here. It needs to be on here. Sorry about that. Okay. If you just had, so here I'm going to run a claim by you, and I'll give you an idea about how to prove it, but I don't want to take the time to prove it. You'll recall that the limit as n goes to infinity of 1 plus x over n to the n is a representation for e to the x. The limit as n goes to infinity of 1 plus t squared over 2n to the n is therefore, like this is like your x now, is e to the t squared over 2. That's kind of what I have going on over here, but I have this extra term. The extra term is going to 0, but, so is this, right? When you compute this limit, you're not allowed to say, as n goes to infinity, this goes to 0, so I'm talking about 1 to the n as n goes to infinity, which is 1, because limits don't work like that. You have to consider all the parts moving at the same time. But even though this term is going to 0 and this term is going to 0, I claim that this second one is going fast enough that it's not going to change the limit, so that the limit of this thing is going to equal the limit of this thing. It's going to 0 kind of fast because as n gets large, this n in the denominator is driving that whole fraction down to 0. At the same time, the a sub n's that are going to 0 are also driving it down to 0. And so I claim that those two things, the n and the a sub n, moving where they're moving, is knocking out this whole term fast enough to get the limit of this moment generating function equaling the limit if we drop this term. So I don't know if you've ever looked at, like, broken this apart, but you might have taken the limit of the log of this and then brought the n down front. Powers and logs do that nice thing. and then taking the limit on both sides and used L'Hopital's rule to get to this result. You could do something very similar here with this much uglier term, and that would be how you would show my claim here. So let me get rid of this mess. Let's look at the limit as n goes to infinity of mzn of t. This is the limit as n goes to infinity of 1 plus t squared over 2n plus an t squared over 2 sigma squared n to the n. And I claim that we could show that this is the limit as n goes to infinity of 1 plus t squared over 2n to the n. So that's going to take some marginal convincing, but I don't want to drag that through the proof today. And if you believe this is e to the 1/2 t squared. So our zn's, as defined in the central limit theorem, which is x bar kind of standardized, its moment generating function looks like this. And I will just remind you that if you're talking about a normal mu sigma squared distribution, the moment generating function, leave myself enough space. Whoa, come back. The moment generating function is e to the mu t plus 1/2 sigma squared t squared. So if you match or compare this and this, you can conclude that this is the moment generating function for the normal 0, 1 or standard normal distribution. So we wrote down the moment generating function for the Zn, we took a limit, and we get the moment generating function for a standard normal distribution. And this is enough to say, thus, the Zn's are converging in distribution to Z, where Z has a standard normal distribution. That's what we wanted to show. So we are done with our proof of the central limit theorem. Okay, let's look at x bar and its asymptotic behavior again. We do have from the central limit theorem that x bar is asymptotically normal with mean mu and variance sigma squared over n, which, by the way, those are the mean and variance respectively for x bar, regardless of whether the sample size is increasing or regardless of what's going on, even if we can't use the central limit theorem. But this means that x bar minus mu over the standard deviation sigma over the square root of n is converging in distribution to the normal 0, 1 distribution. And this means that x bar minus mu over sigma, now this is less technical, but this random variable acts like a normal 0, 1 random variable for large n. So there is the approximation that the central limit theorem is always using. It's always saying, well, let's treat x bar as if it has a normal distribution. But really, it doesn't until you get to the limit. And in most data science applications, large n, most books and papers will say that n is greater than 30, or maybe n is greater than 40. In my opinion, they're both horrible approximations to infinity, but they tend to work kind of well. And I have a question in the chat about how fast this is converging. And it is completely underlying distribution dependent. So the x1, x2, et cetera, were IID. And for some distributions, this is going to converge quite quickly. It's going to look normal with single digit n's, and with some of them, it's going to take a very long time. So that's not something I can answer in general without talking about or looking at the underlying distribution. But these tend to work well. Now, in this class, I'm not going to try to trick you and give you an n of 35 or 29. I will make sure it's a large n. And mostly, we will not have numbers anyway, because this is mathematical statistics, where theory rules. But from this, we also see that if we take, let's look at this again, x bar minus mu over sigma over the square root of n. This is 1 over n, the sum as I goes from 1 to n of xi minus mu over sigma over the square root of n. I am going to multiply the top and bottom by n. And what I end up with is the sum. We're sort of undoing what we did before. The sum of the xi minus n mu over. So once you deal with all your square root stuff, you're going to get sigma times the square root of n. And if this is converging in distribution to the normal 0, 1, then so is this, because it's the same thing. And so this tells us that the sum as I goes from 1 to n of the xi, when you start with some iidx's with mean mu and finite variance sigma squared, the sum is asymptotically normal. So we don't have to be talking about the sample mean. And the asymptotic mean is the thing you had to subtract to make it go to a normal 0, 1, and that's n mu. And the asymptotic variance is the square of this standard deviation term. So this is n sigma squared. So this is another way you might see someone using the central limit theorem. This is a completely equivalent result. Central limit theorem. So let's take a step out of our theory for just a few minutes and talk about some computations with normal distributions, like how to find probabilities for normal distributions. So if we have that a random variable x, I have no sequence at this point, is normal with mean mu and variance sigma squared, this implies that x has a PDF f of x, which is 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared x minus mu squared, and x goes everywhere from minus infinity to infinity, which is why I'm not putting down an indicator. I'm pretty sure I mentioned before that I know we've mentioned several times that this is the bell curve, and it is centered at mu, and that picture is supposed to look symmetric. And if you do the calculus to see where, like here, the function is concave up, and then it goes to concave down, and the point of inflection where it changes concavity is one standard deviation away from the mean. So you can show that by taking derivatives and figuring that out. It's not so hard. But you can definitely see why increasing a variance, which would be increasing a standard deviation, is going to pull those points aside and get you like a flatter distribution, and decreasing it is going to get you something much skinnier. Those are all supposed to look like symmetric bell curves. They're pretty bad. We could show that the integral from minus infinity to infinity of f of x dx is 1. And if you want to do that, I think the easiest way to do it is switching to polar coordinates. I don't really care about it in here. If you want to come on my office hour and recall polar coordinates, we can do that. But let's talk about the CDF. That's going to be an f of capital X, and that's supposed to be minus infinity to x of the PDF. And there's a problem here, and that is we can't do this integral in closed form. There is no closed form expression for the CDF for a normal distribution. So if you want to compute probabilities, you have to do some numerical integration. Now, historically, especially way back, when we didn't have computers, that was not an easy thing to do. So some people worked out integrals and tabulated results. And so that you can look it up in a table, but you would need a different table for different parameters for, this mean, this standard deviation, this mean, this variance, as you change them. So that would be annoying, right? But we kind of already know, I want to stress it today, that we can take any normal random variable and kind of recenter and rescale it so that it's still a normal random variable with mean 0 and variance 1, and then rely on someone's tabulated results for numerical integration for the CDF. So I'm going to talk about that in a moment, but I just wanted to say that you might be thinking we don't need to do this anymore because, we have computers and we have good computing power. But there's a lot of theoretical reasons for us to want to relate a normal random variable to a standard normal random variable. So I think it's super, super important for us to talk about this, even though you could do numerical integration. So let's do it. Sorry about that. So remember, we're using a capital Z to denote a standard normal random variable, a random variable with a standard normal distribution. It has mean 0 and variance 1 and a bell curve shape for its PDF. The CDF for the standard normal distribution is generally denoted by a capital Phi. There's nothing wrong with using a capital F, but it's just so important it gets its own name. So I can't guarantee, everyone uses this, but I can't guarantee that you're not going to see a phi being used for something else or that someone is going to use an F here. But it's really, really common to use a capital Phi. So like of Z, this is going to be the probability that Z is less than or equal to a little z. So that's just notation, notation. And if we have a random variable x with a normal mu sigma squared distribution, if you subtract its mean, I didn't mean x bar. If you subtract its mean and divide by its standard deviation, that gets you a normal 0, 1 distribution. And these values are tabulated. So if we want to find probabilities for something like this, we would compute this and standardize it and turn it into a z and look in a table. So I am making this sound way too hard. Let's get some values here. Let's go back to just the standard normal z. And suppose you want the probability that z is less than or equal to an actual number. Here we're seeing numbers and math stats. Someone mark this day. So we're going to go to a table just to say we've done it and we can read it. And I have a Z table here. You can get it off of the Canvas page if you want a copy of this. And you can see that it's using the same notation we just talked about. This is a table of values of the CDF. And it takes arguments, little z, and gives you in the body of the table probabilities. So what did I have? I had z less than or equal to 1.34. How you read this table is you take these digits, the one and the 0.3, and you go down the column here until you get to 1.3. Then you go across to the 0.04 column, and grabbing this number, that is the probability that you want, 0.9099. So that's how you read this table. It's filled with cumulative probabilities. Some tables will have a second page, and it will give you the CDF values for negative numbers. You'll notice there's no options for negative numbers here. So what would you do if you wanted to find the probability that z is less than or equal to, say, negative 1.34? We're math stat people. We can surely handle this. We're going to want to use symmetry of the um, normal distribution about 0. So let me go back to where we were. Now let's compute a few others. So we know that this probability was 0.9099, and we got that from a so-called z table. And if we want to answer a different question, the probability we're less than or equal to negative 1.34, I would just draw the picture, right? Negative 1.34 is down here. We want this sort of area, but it's going to be equivalent to the area up here. And the area in this upper right tail is going to be 1 minus the area below, positive 1.34. So this is 1 minus 0.9099, which is 0.0901. We're not going to, again, use this table very much, but you should be comfortable with using symmetry here. Let's just do one more. By the way, if this is strictly less than, nothing changes, right? This is a continuous distribution, so it doesn't matter. Let's say we want the probability that z is greater than 0.47. I would just draw it. So let's see. So here's 0, and here's 0.47. This is just going to be, this is the same example again. This is 1 minus the probability that z is less than or equal to 0.47. Now, this is literal, like strict and non-strict, but again, if this was strict and this is non-strict, you would still get this number from the table in the same way. I'm making this sound way too hard. So this is 1 minus, and if you go back to the table, you should get table. Yeah, you'll get 0.6808, which is whatever it is. Don't make me subtract live. Okay, so these are how we get cumulative probabilities for the standard normal distribution. Now, let's make this slightly more, I was going to say complicated, but let's just say more interesting. Suppose that you have a random variable x that is normal with mean 3 and variance 1, and you want to find the probability that x is less than or equal to 2.8. We don't want to carry around, as I said before, a different table as we change the mean and variance. So what we're going to do to compute this probability is standardize the x so that it has mean 0 and variance 1. On the left of the inequality, I'm going to do it symbolically. I'm going to take away the mean and divide by the standard deviation. And on the right, I'm going to do it numerically. I'm going to take away the mean, which is 3, and divide by the standard deviation. So right now, I've got a variance of 1. So I'm just going to write the square root of 1 just so you know that there was a square root taken. And this has a standard normal distribution. So this probability is going to be whatever the probability that z is less than or equal to this is. And this is negative 0.2. So using our table, I'm going to make this, the scale is way off just so I don't have to squish it in. Negative 0.2, we're talking about an area like this, and that's going to be equivalent to the area of being up here, but the table only gives us less than areas, so the area in the upper right tail is 1 minus this total area. And so we can get this probability we want as 1 minus the probability that z is less than or equal to positive 0.2. And you can go straight to the table here. You would go down the side to the row that's labeled 0.2, and then over here to the column that has 0 additional digits. And that probability should be 0.7357. So again, the point is, if you have a normal random variable and you want to compute a probability, you first want to standardize it so that you can call it Z, a standard normal, and then you can use a Z table. I know you're going to use a computer, but you're not going to have to numerically integrate on the computer. All software today can has a function that will spit these numbers out for you. So you're not going to have to set up any numerical integrals that you're going to have to compute. Okay, one more example, and this is with an X bar. So suppose that X1 out through X10 are IID normal with mean 3 and variance 1. And suppose that we want the probability that X bar is less than or equal to 2.8. Well, we know that X bar has a normal distribution with mean mu and variance sigma squared over n, which in this case is 3 and 1 over 10. So let's standardize. This is equal to, now usually people don't write this next line. They jump to the next part, but I just want to be real clear the first time we're seeing this. We're going to subtract the mean for X bar, and we're going to divide by the standard deviation for X bar. The mean for X bar is the original mean is 3, and the variance for X bar is the original variance over n, which is 1 over 10. So this is going to be minus 3 over the square root of 1/10. Now, people don't write this usually. Usually, starting from here, they would write, this is the probability that X bar minus mu over sigma over the square root of n is less than or equal to 2.8 minus 3 over the square root of 1 over the square root of 10. And that's what you're going to see. But I always get the question in here, just because we don't work with data that much, people who haven't had data, they start asking, why do you not use the square root of n here and yet you use it here? What we're doing is always the same. We are always subtracting the mean of the random variable and dividing by the standard deviation. It's just that in this case, the mean and the standard deviation, especially the standard deviation as related to the originals, looks different. So I don't know, I'm having a really hard time phrasing things today. But if you look at this and you look at this and you say, sometimes use the square root of n, I am doing the same exact thing every time. I am subtracting the mean and dividing by the standard deviation, but when rewritten in terms of the original parameters, that looks like this. Okay, so now we can call the thing on the left Z for a standard normal, and on the right, I don't know what this is, to going to be negative 0.63. I'm rounding that off, obviously, but if I'm using the table, then that's kind of all I need. And I don't have this one written down. I don't really feel like flipping back and forth. So you can find the probability in the same way. And when I put this video up, I'll give you the final answer. So now I want to introduce a new distribution that I've actually already introduced to you via homework problems, but we haven't talked about it in class. And that is the chi-squared distribution. The chi-squared distribution is simply a special gamma distribution. So X is said to have a chi-squared distribution with, so it has a parameter like all of our distributions do, And the parameter is known as a degrees of freedom parameter for reasons that we will see eventually. So I'm going to write with n degrees of freedom, but that phrase is not supposed to make sense to you at this time. It's just a parameter, and n is a positive integer. If x has the gamma distribution with parameters n over 2 and 1/2. And you'll recall that we parameterize our gamma distribution in one way, and some people parameterize it in another way, with our beta being their 1 over beta. So yes, you may look up the chi-squared distribution and see like a gamma n over 2 comma 2, and it's because they're using a different underlying base gamma distribution. And so this is just a special gamma distribution that comes up a lot in statistics. I would say that the chi-squared distribution is more important to statistics than the normal. But if this is the case, we write that x, squiggly line, has the distribution, and then a chi-squared n. So we're not going to need the PDF for anything. But yeah, let's just write it down for the record. The PDF for x. So right now I'm going to use our gamma PDF, which looks like this on 0 to infinity, but just plug this stuff in. So this is going to be 1 over gamma of n over 2, 1/2 to the n over 2, x to the n over 2 minus 1, e to the minus 1/2 x, and an indicator that says that x takes on values from 0 to infinity. Again, I don't think you're going to need this PDF for anything, but we are going to need the mean and variance. So the expected value of a chi-squared, it's defined as this gamma, and given the way we parameterized our gamma distribution, our mean is alpha over beta. So for us, it is n over 2 over 1/2, so just n. And the variance for the chi-squared n distribution, for our gamma distribution, if you go to the table, you'll see that it's alpha over beta squared. So n over 2 over 1/2 squared, which simplifies to 2n. So this might be meaningful for you to sort of just tuck away as knowledge, but it's certainly easy to figure out as long as you know how to define the chi-squared distribution. You'll recall that cool table I gave you, adapted from Limas, where we had all the different distributions and arrows going everywhere, showing relationships. And it seems that everything is related to everything else, at least tenuously. The chi-squared distribution is clearly related to the gamma distribution, but it's also related to the normal distribution. Here is a result we're going to need. So I guess I'll call it a claim or something. If Z has a standard normal distribution, then Z squared has a chi-squared distribution with 1 degree of freedom. You could show this using the G inverse method, but you really have to be careful because we have a non-invertible function, and it's actually relevant here because the Z does take on negative values. So you could sort of adjust that. I am going to show this using moment generating functions. And this is probably not the first thing that would come to your mind. I'm not sure why you would think of this in the first place. I just know it works out kind of well. It's pretty slick. So let's do it because we don't usually use moment generating functions for anything other than sums of things. But I am going to give this a name. Let's call this, let's say x is z squared, where z is the standard normal. Let's find the moment generating function for x. This is the expected value of e to the tx. X is z squared. Now, try as you might here, you can't simplify this to get it in terms of the moment generating function for z. For example, this is in no way, shape, or form equal to anything like like this. It's just not true. And you might try a lot of things and say, what do I do? What you do is you just do it. The definition for this expectation is going to be the integral from minus infinity to infinity of e to the t little z squared times the PDF for z. And I'm just going to plug in the PDF for the standard normal. So this is 1 over the square root of 2 pi e to the minus 1/2 z squared. This looks pretty good. I mean, we've got 2e to a z squared kind of thing. So let's combine them. I'm going to pull out this. Actually, I probably don't need to pull it out, but I pulled out the 1 over square root of 2 pi. And I'm going to write this as e. I'm going to combine those exponents. And I want to do it in a way that's going to help me pull that integrating without integrating trick. I'm going to try to match this up to a normal distribution. So I do want to start off with a minus 1/2. And then I'm going to write this as 1 minus 2t z squared. So that's equal to the line above. And this looks like the PDF for a normal distribution with mean 0, because I don't have like z minus something squared. I just have z squared. And then the thing in front of the z squared here is supposed to be negative 1 over 2 sigma squared. So it appears that the sigma squared is 1 over 1 minus 2t for this problem. Now, sigma squared can't be negative, so we are going to need 1 minus 2t to be positive. In other words, we're going to need t to be less than 1/2. And fortunately, t being less than 1/2 does include a neighborhood of 0, so that's important for moment generating functions. Let's finish this off by integrating without integrating. I am going to rewrite the integral as 1 over the square root of 2 pi sigma squared, where sigma squared is defined up here, e to the minus 1 over 2 sigma squared z squared. I've taken care of this, but I've put a square root of sigma squared in the denominator, so I'm going to multiply by a square root of sigma squared. And now that integral is 1. So this whole thing was the moment generating function for x. It is the square root of sigma squared. This is the square root of 1 over 1 minus 2t. And for help in recognizing this, note that this is 1 over 1 minus 2t to the 1/2. If you go through your table of distributions, this is looking kind of close to something like this, like a beta over beta minus t to the alpha, although we're not allowed to have a 2t in there. So to make it look right, I'm going to multiply the top and bottom here by 1/2. And then we have 1/2 over 1/2 minus t to the 1/2. And this is the moment generating function for the gamma distribution with alpha equals 1/2 right up here and beta equals 1/2 right in here. And with our new notation, remember our chi-squared n was a gamma n over 2 1/2. So this distribution is a chi-squared 1 distribution. So I started with a standard normal. I claim that when you square it, you get a chi-squared 1. And we just showed it by finding the moment generating function for that squared variable and matching it to the chi-squared 1 distribution. So this is such an important fact for us, and just want to recap it here. If z is standard normal, then z squared is chi-squared 1. Okay, as a final thing today, I want to take a look at the central limit theorem in action. I'm going to work in an actual numerical example. So suppose that I have x1 out through x 100, IID chi-squared 50, and I want to find the probability that the sample mean x bar, which is going to be the average of 100 things, is between 49 and 51. I don't know why I made one an equality. These could both be less than or equal to, they could both be strict. It doesn't matter for a continuous random variable. Oh, and I mean x bar. What is the distribution of x bar? Our x1 through x100 are IID chi-squared 50. And that is the same thing as saying we're using the gamma distribution with alpha equals 50 over 2 and beta equals 1/2. So gamma 25 1/2. Now, what happens if you sum these x's? I'm not sure we've looked at this one yet. If you want to know the distribution of a big fat sum like this, you would use moment generating functions. The moment generating function is going to be the moment generating function for one of them to the nth power, in this case, the 100th power. But one of them has this distribution. So this is going to be 1/2 over 1/2 minus t to the 25 to the 100, which is going to be 1/2 over 1/2 minus t to the 2500. So let me write that down. We now know that the sum from 1 to 100 of xi has a gamma distribution with parameters 2500 and 1/2. And I don't think that was surprising at all. You can think of the gamma distribution as a sum of exponentials, and so the sum of gammas is the sum of a whole lot of exponentials. So the fact that it's gamma again is not that surprising. We can actually find the full distribution for x bar. So I have two options at this point. One is to say I want the probability that x bar is between 49 and 51, and x bar is 1 over 100 times the sum of the xi. Now I can isolate the sum of the xi by multiplying all the way across by 100. And then we can work with a gamma distribution. If you'd like, you may recall that if we have a gamma distribution with parameters alpha and beta and we multiply by a positive constant c, then we get a gamma distribution with parameters alpha and beta over c. And so from this, I happen to know that x bar, which is 1 over 100 times this thing that has a gamma distribution, is actually gamma with parameter 2500 and then 1/2 divided by 1 over 100. Oh, geez, the real math. So the point is that we can work with, to find this probability, we can use the fact that this has a gamma distribution. Or if you find it easier, you can work with the sum. So since I already set it up this way, I think I'll continue to work with the sum. But I could continue with x bar all the way through and not multiplying all the way across by 100 and using the fact that x bar itself has a gamma distribution to complete the problem. But yeah, I'm just going to stick with what I've written. I am just going to make this a little cleaner and say, I'm going to give that sum a name. I'm going to call it W. W is my favorite letter for a gamma, where W is gamma 2500 and 1/2. So this probability is going to be the integral from 4900 to 5000 of this gamma PDF. So 1 over gamma of 2500, 1/2 to the 2500, W to the 2499, e to the minus 1/2 W, dW. This is 2,499 integration by parts. This is not something I want to do by hand. And in fact, it's not something I want to do with a computer. If you go into, say, Wolfram Alpha, and you're using the free version online, I don't think you can compute this in the given time. If you upgrade to Pro and you have a longer time to crank through it, you can compute it. I did that, and my computer actually made some noise like, but it eventually came up with the answer. So this was doing this numerically. I got 0.6827. And this problem, we were lucky. We knew the distribution of the sum of the x's. We don't always know that distribution. Why did I bring this up right now? Because we could try, instead of doing all of this work, the central limit theorem. So now let's approximate the probability that x bar is between, I keep changing these, between 49 and 51 using the central limit theorem. Incidentally, in your homework, if I'm asking you to find an approximate probability, it's going to be a central limit theorem problem. It's our only approximation. I will remind you that x1 through xn were IID chi-squared 50. That makes the mean, which is the expected value of any one of them, equal to 50. Remember, we just showed that the mean for the chi-squared n is n. And that makes the variance for any one of them 100 because it was 2 times n. And so for large n greater than 30, in our case, n is 100, so we're okay. X bar is approximately normal with mean mu x bar equaling mu equaling 50 and variance sigma x bar squared equaling sigma squared over n, that's an n, which is 100 over 100, or 1. So let's go for our approximate probability that x bar is between 49 and 51 by standardizing it to an approximate standard normal. This is going to be 49. Let me do the center first so you see the symbols. X bar minus the mean for x bar, which is mu, over the standard deviation for x bar, which looks like this. And then on the left, I'm going to actually subtract off the mu and divide by the, so I can just do the standard deviation of this, or if I stick with this kind of notation, this is going to be the square root of 100 over the square root of 100. I'm going to do the same thing on this side. And so now I can say this is approximately, and I have a z in the middle, where z is normal, 0, 1. On the left, I get -1, and on the right, I get +1. So how can we compute this using our table? I want the probability that I am between -1 and 1 for the standard normal distribution. So I really want all of the area to the right, or sorry, to the left of 1, and subtracting out all of the area to the left of -1. I can get these from the table. And let's go real quick. I'm running out of time here. So if I look up 1.00, I get this 0.8413. And then we're going to get the other one using symmetry. This is going to be 0.8413. And then this other one is going to be 1 minus 0.8413. And when you subtract here, you get 0.6826. That's our approximation using the central limit theorem. How does it compare to the exact answer, which has been rounded, but otherwise an exact answer, 0.6827 versus 0.6826? That is pretty darn good. So I'm not even sure that you can do the integral we did up here unless you, the integral I did the long way, unless you have enough computing power. And if we change the problem just a little bit, you won't be able to do it at all. So we use the central limit theorem to get an approximate probability for x bar, treating x bar as an approximate normal random variable for quote unquote large samples. That means n greater than 30 or 40. And it did pretty well. So next time, we are going to talk about the delta method for convergence in distribution. And this is a way for us to talk about like x bar. I don't have a setup here. I'm kind of rushing, but we know it converges in probability to the mean of the original distribution by the weak law of large numbers. And therefore, we know it converges in distribution because convergence in probability always implies convergence in distribution. And so we know things like x bar squared converges in distribution or in probability to mu squared, and that's by the continuous mapping theorem on convergence and distribution. But my question for you is something like x bar squared, does it have a so-called asymptotic distribution? What would that be? That's what the delta method does. It's going to help us find an asymptotic distribution, which is a different kind of statement than what does this converge to? So I hope you come back. It was a little confusing today, and I will see you next time on Mathematical Statistics.